table on the board. Like, let them just see it. These are some more practice problems. These reflect the problems we're doing now, but this does go up to 14.6. So these extra practice problems. They complement the problems from like the problem set. But they're good practice. Have these in Canvas too.
Professor, can I get one?
Yeah, sure.
Oh, you got one?
Oh, yeah, I'll bring you one.
Hey, I got it.
Oh, thank you. I'll hit the lights. Okay, here's the question. We're going to do number 5. This is a heat index. We're all very familiar with this with the summertime right now. You know, the perceived temperature is a function of two variables. And what are they? T is the actual temperature, and H is the relative humidity, right? So you got it. And this is a nice table. It kind of represents that. So everyone, when it's actually 94 degrees outside, but 60% humidity, how does it feel? Right? Like it did sometimes in this classroom. True? Some of those days, I mean, tonight's not that bad, but we've had days where it's felt like this. I mean, it's hysterical, because what about if it's 98 degrees and 85% humidity? This is up at what? Now, 150 and stuff. So it just can get really extreme. So we're going to start with letter A. It says, can you use the table to find a linear approximation to the heat index function when T is near 94 and H is near 70? So the first thing is, let's circle on the table. Where's 9470? 9470, let's circle that number, right? We got that. And I can write down the board. We've got the 94 and the 70, and I can start writing this thing out. L of x and y, right? We need a linear approximation. Except, what were the two variables?
94 and 70.
Rather than x and y, you use t and h. Doesn't matter the order. I'll put t before h. Doesn't matter the order. So now I'm going to write the thing I didn't want you to forget on the test, the z naught, right? There's the z naught plus fx. Okay, I'll say ft. X minus x naught. Okay, I'll write t minus t naught. Plus fh times h minus h naught, bless you. Alright, let me write this again. I'm just looking at numbers we know, and you gotta help me out. Here's my linear approximation. I don't know that. I know this though. What was the number we used?
94.
94 and 70. Okay, minus 94. And this was a what? 7. Oh, we'll get these from the table. No problem. Remember how to get partial derivatives from a table, right? That's my major concern. How do I get that? Great job. Chan right there. What is z naught? Before we had to plug the two numbers into an equation, now we have a table. That's it, right? At 94, 70, f of 94, 70 gives us a value of 118. That's your z naught. We're good on the table. Very good. So now, at least this has some application. We're going somewhere with this problem. We're going to get a linear approximation near that point, but then we can make an estimate that you'll see in letter B. But how do you get this from a table? I do change in f values over the change in the t values, and you get really close to this. All right, everyone, change in f. That's why I'm glad we got this. We can just point to them. These are all f values. There's your t values. Be sure they correspond. So how about right close to the 118? I can do 125 minus 118 divided by 96 minus 94. Or I can do 118 minus 112 divided by 94 minus 92. In fact, I think I'll do both and take the average. So what I'm going to do, what was it? 125 minus 118 over 96 minus 94. What's the other number? 118 minus 112 all over
94 minus 92.
94 minus 92, because that's what the author does. He takes an average of both sides. So what's that? 7 halves? And that's 6 halves? What's the middle of 3 and 3.5? That's what I'm using. So So I'm just gonna draw an arrow and go, there's your average. Just taking the average of those two numbers. But yes, absolutely, students always ask me, can I just do one side or the other? I'm fine with that. I just wanted you, I know you practice out of that textbook. I don't want you to be thrown off like, well, I only got 3, I did the right, why does the book say 3.25? He always takes an average off each side of those. Hey, how about FH? Changing F's over the changing H numbers. What was the calculation? There's the H's. 118, let's use the 70 and 65, or the 75 and 75. 118 minus 114, or 70 minus 65. And, what was the other side? 122 minus 118 all over. 75 minus 7. I just want to point to it so one sees. I'm doing change in F over change in H. Change in F, change in H, right at that point. Take the average of these two. That's 4/5. What's that? 6/5? No, that's...
4/5.
Is that 0.82?
Yeah.
So what's the average of a 0.8 to
0.8.
And we got it. And here's the answer to letter A. This is called the linear approximation. Right? That's the linear approximation. You know that. But there is a part B, and that's what we're getting to. Why are we doing this? Because there's numbers not in that table that we can predict. And you might have guessed, but we're going to get a really good prediction. They said use your linear approximation and estimate the heat index when the actual temperature is 95 and the humidity is 72. So what do I simply do?
Just plug them in.
That's right. So this is going to be part B. Plug them in. What is L of 95? This is calculus 3. Just functions, multivariable functions, linear approximations. 3.25, 95 minus 94 plus 0.8 times 72 minus 70, and here's what I get. What's 118? This is the one time I don't distribute, because that's just 3.25. And what's 2 times 0.8? 1.6. So what's that all add up to?
122.85.
122.85, this is degrees Fahrenheit, and that's the perceived temperature, heat index. Like that a couple times for sure. At least you're on 5 o'clock. You look at that? Hey, everyone, great job with that. There's a, before we do talk about 14.5, there's one more thing from this section. You won't see it in a problem set, but you will see it. It's problems in the textbook, and I didn't want it to throw you off. It's called a differential. So I'm going to go back to Calc 1. I'll turn this off. Turn that off there. I'm going to hit the lights here. But do you recall in Calc 1 on dy dx equals f prime of x? Of course you do. But you know what dy equal to f prime of x dx was called? In Calc 1, they called this a differential. The d1. There's one more thing included in section 14.4, and it's differentials. And I just wanted to make sure, we'll do one problem together. Just so if you're reading a textbook, I don't think I had one of these in a practice set. I don't believe, but just in case, you'll be comfortable with this. That's called a differential. The dy is the differential. It's equal to f prime of x dx. Okay? In Calc 3, it's called the total differential, so it should be just like that. So the total differential is, and this is still in section 14.4, but it's the last part of 14.4, the total differential is dz. And we equal the partial derivative of f with respect to x, I can do the partial of z with respect to x, times dx, plus the partial derivative of z with respect to y, times dy. It's just like this. And where this is the partial derivatives. Let me write it another way. dz would equal fx, or zx, times a dx, plus a fy, or partial with respect to y, times a dy. That's called the total differential. dz is called the total differential. That's cool, but it always gives you it's a value that's close to change in z. So let's do one of these problems before we talk about 14.5. Sound good? Cool. So I'm going to take this from the textbook. This is in 14.4. This is number 31. And here's the question. You will not find this hard, but here's what they ask. If z equals 5x squared plus y squared. So there's a function of x and y. And xy changes from and the 2 points are 1, 2 to 1.5, 2.1. They want you to find two things. Can you compute these two values? Compute the values change in z and dz, total differential. So this will be our problem. This is number 31. It's still in section 14.4 though, so I wanted to do this before we move down to 14.5. Okay, can we start with change in z? This requires no calculus. Do you all agree? So change in z, what would that be? Plug these numbers in, get a z value. Plug these numbers in, get a z value, and then subtract them. Right? Z of this minus z of that. That's change in z. They want you to compute both of these because they should be very close to each other. Just like in Calc 1, dy was very close to change in y for a small change in x. We notice a very small change in the xy coordinates. D should be very close to each other. We're going to observe that. We're going to see that. So that's what I just wanted to do with it. All right. No calculus. What do you get for change in z? So really, on this is just, bless you. Get f of 1.05, 2.1, plug it in, and then subtract f of 1, 2, and I'll put the number down. I did it last night. I remember I got 9 point something.
225.
Is that it? 0.9225. Alright. Now this requires calculus. Let's find the total differential dz. Okay, first I'll write out the formula. Get the partial with respect to x, then multiply dx. Get the partial with respect to y, and then multiply dy. Okay. So you might find this easier. By the way, dx is the change in x, dy is the change in y. So what's dx in this problem? You gotta observe it. How much did x change? 0.05, everyone looking at x went from a 1 to a 1.05. Everyone see how I'm getting that dx? Cool, what's the dy? What's the change in these y's? 0.1? Okay with that? Now just get the partial derivatives and plug in the value. What's the partial with respect to x of that? 10x, but what do you gotta plug into 10x? Make sure you plug in the point. Now there's 2 points given. They want, you get this, it's from the point you initially started at. So I need you to plug this in. So if you plug in 10 times 1, what do you get?
10.
10, I substitute a 1. Because I have to plug in this point, I'll circle. Now, get the partial respect to y, but plug in the same point 1, 2. What's the partial respect to
4.
y?
2y.
2y?
That's
I'll write it underneath, but you got to substitute a
2.
2. What's 2 times 2?
4.
So this was at y equal to 2. This was at x equal to 1. This number should be very close to this. Almost spot on. Almost the same. And what is 0.5 plus 0.4? Yeah, I'm just gonna see? Right, everyone? Very close to each other. That was our option. We can see that, don't we? Spread those numbers out, they're going to be drastically different. Because the idea of a tangent plane going off a sphere, it's going to keep the Earth further and further away from the sphere. It only works when it's really close to the point. Cool. Hey, so the last thing we'll do today. 14.5. Chain rule. Well, you all already know the chain rule. This is cool. This is pretty neat. Do you remember related rates problems in Calc 1? They look so intimidating. Do you remember those? The related rates, a ladder was sliding, or a plane was flying over, and you had to find the rate of change or something. So this is the last thing we'll do today. This stuff's pretty neat. Chain rule. So let's say you got a function. Of 2 variables. How about z equals y times e to the xy